Hey everyone, we're going to continue our study of series. We're going to learn two new tests today. And so the first one goes like this. It's called the comparison test. And so we start off with a couple of sequences. So let's let A, N, and B, N be series. And we need these series to both have positive, sequences. I said series. Be sequences. With all terms greater than 0. Right, so the terms of each sequence have to be positive. So two parts to this comparison test. So if how do I say this? So if A sub n is always less than or equal to B sub n, and the sum n equals k to infinity of B sub n converges, then our conclusion is that the series with the A sub n's converges. So let's put it up here. Sum n equals k to infinity A sub n converges. So here's the idea, right? When you have a series that converges, you want to think of it as adding an infinite number of things, and it adds up to an actual number, a finite number. So if you have something bigger, right, where the BNs are bigger, so if the bigger series converges, then the smaller series has to converge also. So there's part A. Part B, if A sub n greater than or equal to B sub n, and sum n equals k to infinity B sub n diverges, then sum n equals k to infinity of A sub n diverges. So the idea here, if you have something smaller, right now the A sub n's are bigger, so the B sub n series is smaller. If the smaller series diverges, the bigger one's got to diverge also. Okay, so the comparison test is nice. When it works nice and quick and clean. So let's look at some examples here. So let's determine whether the following series, sum n equals 2 to infinity, square root of n over n squared minus 1, n over n squared minus 1, converges, or diverges. All right, so here's a series. And it's one that all of our other tests would not help. For example, test for divergence gives us no information. It's not a telescoping series. It's not a geometric series. Integral test, it'd be kind of a pain to use the integral test on this one. You might be able to, but we don't want to. So instead, what we're going to do is use the comparison test. And here's the idea. Let's look at, so remember the comparison test, whether you use part A or part B, requires you to set up an inequality. So that's what I'm going to do. I'm going to look at square root of n over n squared minus 1. And here's what you want to notice, is that this is less than or equal to square root of n, said that backwards. This is greater than square root of n over n squared. All right, so what just happened there, when you have a fraction, you subtract in the denominator. When you make the denominator smaller, it makes the fraction bigger, right? So if I compare these two, right, the denominator here is smaller, which makes this overall expression larger. And then we can say, okay, this is square root of 1 over n when I simplify, which is 1 over n to the 1/2. So we've shown that our sequence here is larger than this sequence, and now we can write our conclusion. Since sum n equals 2 to infinity, 1 over n squared, so let's see, that's a p-series where our p-value is equal to 1/2, that diverges. All right, so here, because we've got p equals 1/2, so does our original n over n squared minus 1 by the comparison test. We showed that our series is bigger than one that we know diverges. So that's how the comparison test works. What you're going to do is you want to compare the one that you've been given to one that you already know the answer to, right? One that's familiar, right? And if you can show that it's bigger than one that you already know diverges, then the comparison test allows you to conclude that it diverges. If you can show that it's smaller than one that is known to converge, then you know that it converges. Okay, so next example. And so same instructions, I'm just going to write down the series. We want to determine whether it converges or diverges. So let's look at sum n equals 1 to infinity. And this is going to be 2 over n squared plus 4n plus 3. N squared plus 4n plus 3. Now, here's the idea. Before I move on, and we're actually going to use the comparison test to show, to make a conclusion about this one. Let's come back to the original one here. When you're using the comparison test, what you really want to do, the idea is you want to compare it to something simpler, something that you already know, you already know something about. So the idea is I wanted to focus on the dominating terms. So as soon as I saw that, even though I didn't say it out loud, as soon as I see this, I know that I'm going to get divergence. And the reason, what I have, the dominating terms give me an n over n squared, which is a 1 over n. It's under a square root. I knew already, as soon as I wrote this one down, oh, I'm going to compare this one. This one is going to behave like 1 over n squared. Almost always, not every time, but almost always, we're going to compare to a p-series. So in this case, we were going to compare this to the p-series 1 over n squared, and so I knew that this is going to diverge right away. I have to still write up the answer, set up an inequality, and then write down a concluding sentence, right? But in the back of my head, I already knew what the answer is. Same thing here. What about this one? Well, the dominating terms here, I've got a 2 in the numerator and an n squared in the denominator. This one's going to converge. It's going to behave like a 2 over n squared, right? So, and I know when p equals 2, we get convergence. So let's say that now. So we know that 2 over n squared plus 4n plus 3 is less than or equal to. So let's see. Now, if you make the denominator smaller, that makes the fraction larger. I just said that. Yeah, that's right. Okay, so let me just write this down now. Let's say it this way. When you increase the denominator, you make the fraction smaller. So, right? So that's why this inequality goes in this direction right there. Okay, so what we have then is that the sequence inside our series is smaller than one that corresponds to a convergent series. So now we can say since sum n equals 1 to infinity of 2 over n squared converges, right here, p equals 2, so does the original one, sum n equals 1 to infinity, 2 over n squared plus 4n plus 3 by the comparison test. We show that the series we were given is smaller than one that we know converges. So next example, let's look at sum n equals 1 to infinity of n factorial over n to the n. All right, and I want to use the comparison test here. Remember, we've looked at this before. The way to analyze things that involve factorials often is to just write out what it means. So let's write it out. N factorial over n to the n. That means 1 times 2 times dot, 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 until we get to n in the numerator. And it means n times n dot, dot, dot times n in the denominator. All right, so we got n factors of n in the denominator. All right, now I'm going to draw a little box here, right there. If you look at the stuff in the box, what we're going to have is a bunch of fractions whose numerators are all going to be less than or equal to the number n, which means that the stuff in the box is less than or equal to 1. Which means that this fraction right here is less than or equal to the leftover stuff here, so this is less than or equal to 2 over n squared. All right, so now what we know is that n factorial over n to the n is less than or equal to 2 to the n. 2 over n squared. We know that 2 over n squared converges, and so we showed that our series is smaller than one that we know converges. So we would say it like this. So since sum n equals 1 to infinity, 2 over n squared converges here because we've got p equals 2, so does the original series. So sum n equals 1 to infinity, n factorial over n to the n by the comparison test. We showed that our series is smaller than one that is known to converge. Okay, so the comparison test is one of my favorite tests, right? When it works nice and quick and clean. It doesn't always work, though. And so let me give you an example here. Let's look at this one. Sum n equals 2 to infinity of 1 over n squared minus 1. Now, this one, I want to use the same intuition that we had before, right? This is going to behave, if we kind of get rid of everything except for the dominating terms, we have a 1 in the top, an n squared in the bottom, so this is going to behave like a 1 over n squared. It's going to converge. But here's the problem, right? If I want to use the comparison test, I start writing down my inequality, right? So I have a 1 over n squared minus 1. How does that compare to 1 over n squared? Well, it turns out, right, that it's actually larger than 1 over n squared. So our sequence right here is bigger than one that we know converges. That's not going to help us, right, when the comparison test, with respect to the comparison test, right? So the comparison test doesn't work. The inequality is just going backwards, right? You want to make, if you want to use the comparison test to show that your series converges, right, you need to show that it's smaller than something that's known to converge. Here we've got it showing that it's bigger than something that's known to converge. So it fails. There's other tests that we could use, right? It's just the comparison test doesn't work. We could use the integral test. You'd have to use partial fractions. So what else is there? Could use the integral test, but the integral test is actually the one that I try to avoid, right? If I can avoid integrating, I'm going to, right? So you could, but you could set it up as partial fractions. It's also telescoping. Once again, by doing partial fractions, you could use the telescoping process to find out that it converges. But that also is a little bit tedious. The test for divergence doesn't help. Right, you get a limit of 0, which gives you no information. It's not It's not geometric, so the geometric series is not going to work. So here's two that I try to avoid, integral test and telescoping. I usually, try to stay away from. The other tests don't work. So so we've got these options, or use a different test. And here's the idea. This one looks so close to one that we know converges, right? That -1 is throwing things off. We can't get the inequality correct to use the comparison test. And so this next test that I'm going to write down says, you know what, this one still, it behaves so closely to 1 over n squared that we're guaranteed it converges, right? And so let's write down this new test, this different test. And this new test is called the limit comparison test. And so it starts off the same, right? We've got a couple of sequences, so let's let a sub n and b sub n be sequences where all the terms are positive. So a sub n's are greater than 0, and all the b sub n's are greater than 0. Now, if the limit as n goes to infinity of a sub n over b sub n is equal to some constant, let's say c, where c is strictly greater than 0. Then either both series converge or both diverge. So then sum n equals k to infinity of a sub n and sum n equals k to infinity b sub n both converge or both diverge. So think of it kind of like we were doing with the comparison test. A sub n, the a sub n series is the one that we're given. And the b sub n series is the one that we already know about. That's the one that we're familiar with. So if we compute, we set up this limit right here. If we get a positive constant, and we know what's going on with this one, maybe it converges. If this one converges, then this one converges. If this one diverges, this one diverges. So let's return to this example we're doing. I'll write it up again. So it turns out that the limit comparison test is exactly what we need. So the limit comparison test is designed to help when you can't get that inequality to go in the right direction. Right? So let's say return to the sum n equals, what was it? N equals 2 to infinity 1 over n squared minus 1. Now, we know that this behaves similar, or at least intuitively, this behaves similar to 1 over n squared, so that's what I'm going to do. I'm going to apply limit comparison test. So, since the limit as n goes to infinity of 1 over n squared minus 1 divided by 1 over n squared, right? So this part right here, the one that we're given, that's playing the role of a sub n, and the one that we're comparing it to, that's playing the role of b sub n, right? The 1 over n squared. And so let's compute this limit. This is limit as n goes to infinity, n squared over n squared minus 1. This is polynomial over polynomial where the degrees match, so the limit is going to be the ratio of the leading coefficients. So that's going to be a 1 over 1, which is equal to 1. So since the limit equals a positive constant, right, here's our c value, and that's 1 is greater than 0, and sum n equals 2 to infinity of 1 over n squared converges, because it's a p series where p is 2, so does our original series sum n equals 2 to infinity 1 over n squared minus 1 by the limit comparison test. So as we're going through these examples, the ones that I do in class, I want your write-ups to look exactly the same as mine in the sense that, for example, when we're doing the limit comparison test, you need to compute a limit. You need to explain why the one that you compared to converges. In this case, it was a p series, so we know that when p is equal to 2, it converges. And then make our conclusion, right? So let's do a few more examples. Next example, let's look at the series. Sum n equals 3 to infinity. 2 plus 3n. 2 plus 3n over square root of n to the 5th plus n. Okay, whenever you're doing the comparison test or the limit comparison test, you kind of want to have an idea of whether it's going to converge or diverge before you even get started. In this case, and the way to think about this is to look at the dominating terms. There's an n in the numerator. There's an n to the 5th under a square root in the denominator. So this is going to behave like an n over n to the 5/2, meaning that I would like to do a limit comparison test in this case. This is going to be limit compared with 1 over n to the 3/2. Right? Focus on the dominating terms. So, it goes like this. Since the limit as n goes to infinity of 2 plus 3n over square root n to the 5th plus n divided by 1 over n to the 3/2 equals limit as n goes to infinity 2n to the 3/2 plus 3n to the 5/2 over square root of n to the 5th plus n. This limit is going to equal 3, right? It's going to be the ratio of the leading coefficients. There's a 3 in the top and a 1 in the bottom. This is not exactly polynomial over polynomial, but it's close enough that you can use that same idea, right? You get the ratio of the leading coefficients. We got a limit equal to 3, which is a positive constant. So since this and, okay, so let's finish our sentence, and sum n equals 3 to infinity 1 over n to the 3/2 converges, because it's a p series, where p 3/2 is greater than 1, so does the original by the limit comparison test. Now, one question you might ask is, how come you didn't use the comparison test? Why did you choose to use the limit comparison test in this case? So when you're setting up, you don't need to write this down, but here's the idea. 2 plus 3n and square root n to the 5th plus n. So remember, what you're doing when you use either the comparison or the limit comparison test, the idea is to kind of get rid of all the stuff and focus on the dominating terms. So it is true that this is less than or equal to 3n over square root of n to the 5th plus n. Right? If you throw away something in the numerator, something positive in the numerator, it makes whoa, 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 craziness. I just wrote the wrong thing there. Sorry. when you make the denominator, when you make the numerator bigger, it makes the fraction larger. Sorry, I said that backwards. But now, when you make the denominator larger, you make the fraction smaller. So notice now we've got inequalities going in two different directions. We can't get our inequalities to match, right? That's why I opted to use the limit comparison test. When you can't get your inequalities to work out, that's when you go to the limit comparison test. Okay, so next one. So sum n equals 1 to infinity, e to the 1 over n divided by n. So let's think about this one. What do you think? Well, e to the 1 over n, as n gets larger and larger, this exponent is approaching 0, which means that, the numerator is getting closer and closer to 1. So this one is going to behave like a 1 over n, which means it probably is going to diverge. So you always want to have some sort of, not suspicion, but you want to have an educated guess on what your series is going to do before you even get started. Right? So I'm going to use the limit comparison test, and it will go like this. So since limit as n goes to infinity of e to the 1 over n divided by n over 1 over n, that's equal to the limit as n goes to infinity of e to the 1 over n, and now as n goes to infinity, exponent's approaching 0, that's equal to 1. So we got a positive constant, and sum n equals 1 to infinity 1 over n diverges, right, because p equals 1. So does the original. Put it up here. By the limit comparison test. So both of these tests are kind of fun to apply. They work out nicely. Much cleaner, much easier to deal with than the integral test, right? The integral test is one that I tend to avoid. If I can avoid integrating, I do. Sometimes you're stuck, that's the only one you can use is the integral test. But if I can use the comparison or limit comparison test, those are the ones that I'm going to pick. Okay, so let's do a couple more examples. Next one, sum n equals 1 to infinity. 3 plus 4 to the n divided by n. Oh, shoot. Yeah, actually, I can't put an n here, can I? Never mind. Let me fix that one. Like that. 3 plus 4 to the n divided by 5 to the n. So what do you think here? Well, okay, this 3 in the numerator really isn't going to have that much effect, right? Overall, the dominating terms here are a 4 to the n and a 5 to the n. So in this case, I actually can get an inequality that works like this. So 3 plus 4 to the n over 5 to the n. Who do we want to compare this to? Oh, sorry, I need to set up my limit. So let's write it like this. Limit as n goes to infinity of 3 plus 4 to the n over 5 to the n divided by 4 to the n over 5 to the n. I want to focus on the dominating terms, which means get rid of that 3. This limit as n goes to infinity. So if I flip and multiply, what we have is 3 plus 4 to the n over 5 to the n times 5 to the n over 4 to the n. This limit is going to come out to be 1. And so what does that tell us? It tells us that both series do the same thing. All right, I mean, you can cancel the 5 to the n's if you're wondering why. So what do we get? I guess I kind of skipped a step there. Let me cancel those and actually work this out. So this limit, it's going to be limit as n goes to infinity of 3 plus 4 to the n over 4 to the n, right? That limit's definitely equal to 1, right? So since sum n equals 1 to infinity of 4 to the n over 5 to the n converges. Now, how do I know this? This is a geometric series, right? So this one converges. This is the first example where we weren't comparing it to a p-series, right? By the geometric series test, I know that this one converges. So does our original. By the limit comparison test. Okay, so let's do one more example. And this one is a little trickier. So sum n equals 1 to infinity of tangent of 1 over n. Now, this one may or may not look familiar. In fact, this one's a little bit more obscure, I guess. But what you want to remember, and I think I had this on the quiz last time, what we know, I think I started it off like this, n times tangent of 1 over n. And that is tangent, or that can be written as tangent 1 over n over 1 over n. And on your quiz, you show that this limit, right, is equal to 1. Yeah, that's right. This was on a quiz. And so here's the idea then. That limit right there is going to equal a positive constant. So what I'm going to do is I'm going to apply the limit comparison test to this one, where we put 1 over n in the denominator. So since limit n goes to infinity, tangent 1 over n over 1 over n, right? So this is one where you can apply L'Hopital's rule, right? We have a 0 over 0. So this, by L'Hopital's rule, that's limit as n goes to infinity, negative 1 over n squared secant squared 1 over n divided by negative 1 over n squared. Cancel that stuff. That's equal to the limit as n goes to infinity, secant squared of 1 over n. As n goes to infinity, inside is approaching 0, so we get secant squared of 0, which is equal to 1, right? So we did the limit of this ratio right here. We got a positive constant. That means that both series do the same thing. So, since sum n equals 1 to infinity, 1 over n diverges, that's the harmonic series, p equals 1. So does the original series by the limit comparison test. So this one, it's a little less obvious, right, that the limit comparison test is the right thing to do. But if you remember that limit that you computed on the quiz, it should make sense, right, that this is something to try. And sometimes you just got to try things, right? Doing series and sequences, or just trying to decide whether a series converges or diverges, can be tough, right? Sometimes you got to try various things. Sometimes more than one test works, right? So anyways, you got some homework problems to work on this stuff, And so we will see you next time. All right.